So let me show you a few more examples of classical historical experiments. And this time I'll try to contrast the pre-computer approach with the post-computer approach. So the first example is a very famous one. It pertains to numbers of this form, 2 to the k plus 1. If you sit down and check, and you don't really need a computer for that, you can see that 2 to the first plus 1 is a prime, 2 to the second plus 1 is a prime, 2 to the fourth plus 1 is a prime, 2 to the eighth plus 1 is a prime, and 2 to the 16th plus 1 is a prime. And you can actually also quite easily prove that if 2 to the something is a prime, then this something has to be a power of 2. So this combination of the 5 observations above and the lemma led Fermat to the conjecture that every number, so-called Fermat numbers, Fm, 2 to the 2 to the m plus 1 is a prime. So this, of course, was an experimental discovery coupled with, I guess, some sort of idea that this could be an if and only if statement that the lemma has here. And as I'm sure you know, this is one of the very false conjectures of the early history of math. In fact, Euler again proved not so long after Fermat that f5, so that's 2 to the 32 plus 1, which is this number down here, is not a prime. Indeed, 641 is a factor. So to perhaps contrast what Fermat and Euler did with the tools that we have at our disposal in this course, let's try to look a little bit at this problem in Maple. So Maple is the program that we're going to use for our experiments. As we will come back to later, there are some weaknesses with Maple, and that means that we cannot rely on Maple exclusively as sort of full-time experimental mathematicians. But for the purposes of this course, we've decided to work with Maple simply because it's a program that all of you have direct access to. If you don't have it already, you can download it for free from the university homepage. And also, it does a lot of things that we're going to want to do very easily. So this will simply be the place that we're going to work in. And before I start, let me say a little bit about how I'm going to work with Maple. So those of you who know Maple well will also know that there's two fundamental ways of using Maple, the so-called worksheet mode and the document mode. The worksheet mode is the old-fashioned one, and the document mode is a more modern one, which has the advantage, I'm talking about the document mode, that it produces something that looks a lot like standard mathematics. So you can actually write a paper and solve an exercise directly in Maple, print it out, and it looks like a fairly standard math. But for the purposes of this course, it's clearly advantageous to use worksheet mode. If you have a Mac like me, I don't think you'll have to do anything else and choose worksheet mode when you start Maple. But it is possible. So sorry, this is in Danish. But if you go to the preferences, you can sort of set it up so that you prefer to use worksheet rather than document mode. And if you want to use worksheet when you document when you solve your exercises, that's fine with us. But whenever I make something for you, and certainly in the textbook that we're using, we will stick to the worksheet mode because it's very clear precisely what it is that I'm inputting and what comes out as output. And so to make that distinction, it is better to use use worksheet mode. So essentially, let me address the problems of Fermat numbers using now Maple, and I should mention that we're going to come back to all of these things, so I'm just giving you a taste. So first of all, I will define a function that computes the nth Fermat number, so that will be 2 to the m plus 1, like this. And now it's very easy to compute these numbers, the Fermat numbers, say from 0 to n, I should use m, from m equals 0 to, let's say, 13. But I'm just showing you, first of all, it's very easy to compute these numbers using Maple, but also, as you can see, these numbers become very big quickly. So the first 5 numbers that actually are prime, as known to Fermat, are those ones, and you'll see that simply because it grows like a double exponential, then the length of these numbers roughly will double. So this is a number proved by Euler to be composite. And as you can see, I mean, I only printed 13 numbers, so the last number, which is down here, is sort of a whole screen full of numbers. Right, so I can try to investigate whether or not these are primes, and this is extremely easy. In Maple, there is a command called isPrime, and so I will just ask Maple, is the mth Fermat number from 0 to 13 a prime? And you can see that Maple doesn't even have to think very long about this problem, so it will confirm that the first 5 numbers are primes, but then these numbers going on further on are all composite, Maple says. Right, so this actually means that when we're using the tools that are at our disposal, and you can see I haven't really tried to use Maple big time here, I'm just making a quick little experiment, but it would actually seem more reasonable to make a conjecture which would be more or less the opposite of what Fermat thought, namely to say that the first 5 Fermat numbers are the only Fermat numbers that are primes. And in fact, this is, I don't know if that's anybody's conjecture, but certainly when you have a Fermat number for which it's known whether or not it is prime, then it is known to be composite whenever the index is from 5 and upwards. So you see that the very simple-minded mathematical experiments that we're doing here compared to the very simple-minded experiment that Fermat did lead to sort of obviously different conjectures. Right? So this, of course, has something to do with the scale of the experiment that we can use. We can use a computer to do these computations, and of course, it would have been very, very difficult for Fermat to figure out if this last number here, for instance, is a prime or not. So let's take another example. So this is a copy of a letter by Gauss to Encke, a German mathematician he was communicating with or corresponding with. This is Gauss discussing the so-called prime number theorem, where he is interested in how many primes are there under a certain number. So Gauss looked at the number of primes under 500,000, which is 41,556, under 1 million, and so on. These numbers actually, as we will see in the exercise, are not completely correct. Gauss had various tables of primes to do this, but they were not entirely accurate. In fact, as is also described in more of the letter. But you can see that Gauss then compares these numbers to the integral of 1 over log u, and indeed the differences are quite small. And then he's comparing it to another attempt by Encke. So this is quite clearly an example of an experimental approach that Gauss is simply counting primes, and then he's looking at some sort of pattern in order to try to come up with an estimate or a theory that describes how many primes there are. So to be a little bit more precise, Gauss made this conjecture. So if you say pi of x, which is common in number theories, the number of primes less than x, I mean, x will most likely be an integer, but it also makes sense if it's not. Then Gauss had the idea or the conjecture that that would roughly be the integral from 2 to x of 1 over log u. And this is called the logarithmic integral of x. Right, so this was a conjecture. This, I should point out, by the way, that Gauss was a teenager when he made this conjecture, but it was simply based on looking at the distribution of primes. So he would look at some intervals and then say what is the proportion of primes in this interval compared to the, say, the center of the interval. And this seemed to decay roughly as 1 over the logarithm of u, and then if you sort of just integrate up, you'll get this conjecture. And this was actually, this turned out to be correct, and it was proved about 100 years later by independently by Adama and de Vallée-Poussin in 1896, that this relation is true in the sense that, for instance, if you look at the quotient, then as x goes to infinity, you'll get a 1.